In section 10.7, we're looking at a rigid object that is under a net torque. So we no longer are necessarily looking at equilibrium situations, but where there might be some sort of a torque that is now creating some sort of angular acceleration. We want to understand the connection between force and torque, and also to be able to identify various torques acting on a system and apply our rotational concepts to solve problems involving net torque. So far we've looked at a rigid object in an equilibrium. But what would happen if there was a net torque, an unbalanced torque in some direction? Let's imagine that a rigid object has this collection of particles, and we want to calculate the net torque by summing the torques on each individual particle. Remember, if we were looking at this mass m as being a piece of a rigid object and maybe a force acting in the direction that we see here, it's really only the tangential component or that perpendicular component to that moment arm that's going to actually create any sort of torque. So you can see here that we have our F equals ma equation, where we're looking at just the force in the tangential direction and therefore just the acceleration in the tangential direction. And now we can multiply both sides of that equation by r. That is, again, the distance from the axis to the particle that is rotating. So that would be like our lever arm for this torque that is acting on the object. Since we know that A can be rewritten as R alpha, we can put in another r, so our r is now squared, and we have an alpha there, and this rf becomes torque, and this mr squared, when we sum up all of the torques and all of those little bits, the alpha value is going to be the same for every little bit that is a part of this object. So that can be pulled outside of the summation, and we're really left with a summation of that mr squared. And remember, the summation of mr squared is actually equal to the value of I, or that moment of inertia. So since these internal forces would all cancel out, we'd really be left with the sum of our external torques being equal to I alpha. Just like every other equation that we've come across so far has a translational counterpart, this one also does too. You'd be able to look at this as an F equals ma, but instead with this being done in rotational variables. Torque is like your F, M is like your moment of inertia, and of course A and alpha are kind of those pieces that match up. Now remember, we had that work kinetic energy theorem that said that the work done on a particle was just equal to the change in its kinetic energy. The same will apply to rotation as well, where the work done by those external forces is equal to the rotational kinetic energy, or the change in the rotational kinetic energy of the object, as long as we don't have energy going into any other forms, like a stored form in a potential energy. So let's kind of look at this really quickly and prove how this can actually be true. Remember that work is an FD, right? And if we were to look at just a little bit of work done by a torque on a system, that little bit of work would be an F times a ds, a little change in a position. Now again, our force is going to be an F sine of phi. Why is it the sine of phi? That's because only the tangential component causes any sort of displacement of that object or any kind of rotation on the object. So looking at this as the piece of the force that actually creates some sort of rotation or change in the position, and taking this ds and rewriting it as an r theta, because s is equal to r theta, we now have this equation here. Now we can rewrite this because we know that f sine theta times r really just is the torque on the object. And so really we're left with any little bit of work being equal to a torque d theta. Now note that this is the product of torque and an angular displacement. Just like work is equal to Fd, we see that work here is equal to a torque times a angular displacement, or a d theta. So using the rotational form of Newton's second law, knowing that torque is equal to an I alpha, we can rewrite alpha as d omega dt, and then we can take our values that we have here and just sort of rewrite them a bit. All we're doing here is taking our expression and our I alpha that we have right here and multiplying it by the d theta. So we're just taking torque and multiplying by d theta. So we're just kind of separating these variables a little bit, and that's what you see in the next step, so that we can simplify this and actually rewrite the entire expression as an I times a d omega d theta times an omega, because really d theta dt just is omega. It's the same thing. So now that we know that our torque times a d theta is a little bit of work, we can multiply this piece here, this is our torque, by a d theta, and we could cancel those things out so that we end up with this expression here. And now we can integrate both sides of this expression in order to come up with a value for work. And when we integrate I omega d omega, we really just get a 1/2 I omega squared. And so we end up with this rotational counterpart to that work energy theorem. Just like we said, work before was equal to a change in this 1/2 mv squared quantity for kinetic energy. We now look at rotational kinetic energy as being the 1/2 I omega squared, and work being equal to the change in those values. So just like energy considerations made problems easier to solve when we worked with translational motion, the same can be said of rotational problems as well. When we're working with an expression where we're trying to figure out a work or something like that, it may be easiest to find that amount of work by looking at the change in the rotational kinetic energy. This expression looks the exact same as it did for the work kinetic energy before when it worked with translational motion. We simply had a 1/2 mv/f squared minus a 1/2 mv/I squared. Now, if a system is both translating and rotating, then our work might be a combination of changes in both a translational sense and a rotational sense. Essentially, what we would be looking at there is looking at this object having a 1/2 mv squared, where that v is the velocity of its center of mass, and the object might also have a rotational kinetic energy of also having a 1/2 I omega squared. And we could look at both of these types of quantities and the changes in both of these quantities to figure out an amount of work done. We could also look at the rate at which work is done. If work is equal to a torque times a d theta, we could put both of these expressions over a dt and now talk about the amount of power associated with this, where d theta dt is really just omega, and we now find that power is equal to torque times the angular velocity. This is the same thing as when we said that instantaneous power was equal to an FV. Again, the equation looks the same, but with those rotational counterparts placed in. Instead of F, we have torque. Instead of V, we have the omega. Let's now try a problem where we will have a net torque that is creating some sort of acceleration. Here we're looking back at the Atwood machine example. We did Atwood machine problems before, but they were a simplified version. The Atwood machines we worked with before were frictionless. In this case, we have the Atwood machine set up on a pulley with a mass M and a radius R that is not frictionless. That means that the string is not just going to slide over the surface, but instead this string will cause the pulley to actually rotate and turn. So maybe we will have our pulley rotating in this direction. Remember, counterclockwise is what we always call the positive direction. Now, because this thing has to be rotating and the string is simply not sliding over the top of it, that rotation has to be caused by differing torques. And those differing torques will only be there when you have a different tension on each side of the rope. So when we set up our forces that are acting on these objects here, like the weight of block 1 and the tension pulling it back up, the tension on one side of this pulley is going to be different from the tension on the other side. So we are actually going to label these T values as a T1 and a T2. And in fact, when we look at the pulley itself and the forces that are acting on it, if this was our pulley here, we would have tension 1 trying to pull the pulley down in this direction, and tension 2 trying to pull the pulley down in this direction. It is in fact these different tensions that result in different torques on either side of the system, and those different torques actually create the rotation that we're looking at. So again, we want to set up a couple of equations. First of all, let's sum up all the forces that are acting on object 1. On object 1, again, we need to define direction here where this is positive, moving in the counterclockwise direction, and anything going in the negative direction will be that clockwise direction. So on block 1, we have M1G acting in a positive direction and its tension acting in a negative direction that we can set equal to M1A. When we sum up the forces on object 2, we have our tension acting in the positive direction minus the weight of block 2 acting in a negative direction that we can set equal to M2A. Now what I want you to notice here is that we have at this point set up two equations. When we used to do these Atwood machine problems, these were the only two equations we needed because our tension values were the same. In this case, these tension values are not the same, which means that we actually have three variables because each tension value is a variable and the acceleration of the system as a whole is also a variable. Now, because the system is connected by a string, that acceleration will still be the same for block 1 and block 2 and the pulley, but the tension values will be different. Because we have three variables, that means that we actually need three equations. So let's go to our third equation, which is now going to be the sum of the torques on the pulley. When we look at these torques, again, we want to sum up what is pulling on the sides of this pulley, making it want to rotate. In the positive direction, we have the force T1 multiplied by its lever arm, which is the radius of the pulley. On the opposite end, we have T2 trying to pull in the negative direction, or to create a clockwise torque. And that would be the force T2 multiplied by its lever arm, also the radius of the pulley. And when we sum up the torques, we now know that we can set that equal to I alpha. To simplify this and be able to work with variables that we're actually given, we're given variables of masses and radius, but we don't have an I, and we also don't have an alpha that we would like to stick with. We want to stick with this A like we have over here. So we're going to rewrite I as the moment of inertia of a disk or a solid cylinder. If you refer back to page 300 in your books, you would find that if you were to model the pulley as a solid disk or cylinder, its moment of inertia would be 1/2 mr squared. We also know that since A is equal to R alpha, that we could rewrite the alpha as an A over the radius of the pulley. Now, to simplify things a little bit, we could cancel out some of these variables. For example, having an R up top and an R down bottom, those will cancel. And we also have one R in every single term in this expression, so all of those R's would cancel, leaving us with T1 minus T2 equaling 1/2 ma. Now, to solve for the A, since our goal here is to calculate the acceleration of this entire system, we want to replace these T values with expressions that will have A's in them instead. So if we come back to our first couple of equations, we could rewrite these solving for the tension values. In the first equation, we would find that T1 is equal to M1G minus M1A. So instead of T1, we will write M1G minus M1A. To solve for T2, we can come to our second equation, where T2 would be equal to an M2A plus an M2G. So to come down here, we can plug that in for T2, M2A plus M2G, and set that equal to 1/2 ma. Take a minute, pause the video, and see if you can actually solve for A. Remember, you got to get all of these A's together on one side of the equation, and make sure that you remember to distribute this negative sign through to everything in the parentheses. Check your algebra now and pause the video. When you solve for A, you should find that the acceleration of this system is equal to an M1G minus an M2G all over M1 plus M2 plus 1/2 capital M.